Assalamu alaikum wa rahmatullah. Good morning, good afternoon, and good evening. Uh, Today, welcome to our third lecture in our formation evaluation course. In the previous class, we talked about mud logging, the wellbore stability, and its relation to the mud weight. We also covered directional drilling and the cases in which we use directional drilling. We talked about cementing, and we highlighted both perforation and artificial lift. In this class, we will start talking about formation evaluation, and to start with is that the ultimate objective of well logging in petroleum industry is to identify the possibility of existence of producible hydrocarbon, because we might find hydrocarbon, but it might not be producible, and that's make it unprofitable. So profit is the main important factor in the whole cycle. If you cannot make profit from whatever you are doing, then you are just losing money. So this hydrocarbon, it must be producible. So the definition of a reservoir, already know that it's a rock that contains both porosity and permeability, and those two factors, porosity and permeability, they are highly affected by deposition environment and geogenesis. You already know that we have different type of deposition environment, and each deposition environment is divided into what is called sub-environments, and each sub-environment is characterized by different type of lithologies, and each lithology have its own physical properties and composition and chemical composition. So if we talk, for example, about fluvial environment, in which we have sub-environments like the channel, we have the point bar, we have the sandbar, we have the crevasses play, we have the floodplain. So each one of those sub-environment is having different lithology, and this lithology have specific, as I mentioned, chemical composition. So might be clay, like in floodplain, or shales in floodplain, while it can be sand in the channel itself. So in terms of composition, the composition of the sand is not the same as the composition of the shale in the floodplain, as well as the physical properties, which is the permeability and porosity, are different from the sands in the channel and shales or clays in the floodplains. So that's how the deposition environment play a major role in determining the porosity and the permeability. The diagenesis, it can play a positive or a negative role. So it can either enhance porosity and permeability, or it can destroy the porosity and the permeability. So for example, if some formation or some lithologies are soluble in, for example, water or formation water, that can create or can enhance the porosity of the formation. but those soluble formation which has been carried by those fluids, somehow they will be precipitated somewhere else. So by their precipitation in the pore spaces in some other area, that will block our pore spaces, and that will destroy the porosity and the permeability of that formation. So diagenesis is positive and negative depending on how it's work. So the understanding of those parameters is very, very important prior to any evaluation process. Now, what is formation evaluation? We said that mainly in well logging we are measuring physical properties, not only physical but some other properties as well. So those measurements has to be interpreted in order to understand what's happening in that specific reservoir. So the process of interpretation of those measurements is actually the formation evaluation, and those measurements are taken inside the well bore. So that can be done either through wireline logging or logging while drilling, because if we got those measurements from the logging, either wireline logging or measurement while drilling, and it has been presented in the logs, it means nothing without being interpreted. So it's just the lines within the log sheet, unless we are interpret those measurements in order to understand whatever is happening in the reservoir. We can also understand the fluid content of the rock. We have talked about specific logs, for example resistivity and NMR, that can differentiate between the type of fluids within the reservoir. This point I have already said that this measurement are actually presented in the logs, and we have see that in the previous lecture, and we talk about the log header and the scales and how we read those parameters in each interval or in each depth. Although it's nowadays done by software, but it's very important to know how to read and understand those logs, because in some cases you might need to print it out and do a manual interpretation, and in that case you have to be able to read those informations from the log. So why we are using formation evaluation? To evaluate the hydrocarbon reservoir and to predict hydrocarbon recovery. So and this is the main point of this course. As we are going through the course, we will know how we can evaluate the hydrocarbons and predict the oil recovery, how much oil is there in the hydrocarbon reservoir. The second point is to provide the reservoir engineer with the formation, geological and physical parameters which is necessary for the fluid flow models. And I believe previously I have highlighted the concept of 3D modeling. And in 3D modeling, we have two types of model. We have static model and we have dynamic model. The static model is the model which is basically generated by or created by the geologist, and it's in the basic form. It shows the facies distribution, the porosity distribution, the permeability distribution, the water saturation distribution within the reservoir or within the oil field, if the model is covering the entire oil field, the structure of the structure style and the structure type in the oil field as well. This model, after it has been generated, it's transferred to the reservoir engineers. And in the first lecture we said that there is no step is done by only an individual. There is always the concept of integration. So the work is always done in teams. So after the geologists finished with the static model, it will be shifted to the engineers or to the reservoir engineers. They have their own inputs, data, that will help them to evaluate the fluid flows within the reservoir. And for example, the effect of production of the hydrocarbons in the reservoir on the wells or the nearby wells or the nearby oil field and so on. So you can put the entire scenario for the reservoir during the production, and the life cycle of the whole reservoir during the production throughout the years. We can also measure the fluid pressure and formation fluid samples from the reservoir. It's also very helpful to determine the ability of borehole to produce hydrocarbon. Because, for example, if we have a well in which there is a reservoir that contain a very low effective porosity, that will indicate some problems in the production. So, and then you have to find a way to improve this porosity and permeability of this reservoir in order to allow the production to take place. So all those scenarios has to be evaluated and understood before drilling, before moving from exploration to development to production. The objective of reservoir evaluation, it's in details for whatever I have been saying in the previous slide. So to locate the reservoir vertically within the drill section. As we know, the total depth of the borehole, it can vary very large. It can reach 2 to 3 thousand feet, and we mainly we are not interested in the entire borehole section. So we only have a very limited interval, which is characterized by specific criteria that is make it promising for hydrocarbon production and so on. So in order to move from the entire section of the borehole to the sections which contain reservoir rock, to the injection to the sections which is containing reservoir rock that contain hydrocarbon, and even to go further to uh, borehole sections which is contain reservoir rock that contain hydrocarbon, which is characterized by uh, a good amount of porosity and permeability that allow the production of those hydrocarbons. So we are keep zooming in until we reach to the the zone of interest. Uh, Determination of the fluid types within the borehole, we can do that through the well logs. In the basic way, through resistivity log, differentiate oil water contact and gas oil contact and so on. And NMR can also show us different type of fluids and the movable fluids from immovable fluids. It can also be calculated as well as it can be shown through the NMR. Computation of porosity, total porosity, primary porosity, secondary porosity, effective porosity, and we have discussed this many times, and we talked about the difference between total porosity, primary and secondary and effective, and how each one of those can affect our reservoir. Water saturation is very important parameter to be calculated because it's very essential for the calculation of hydrocarbon reserve. The pay thickness is related to whatever I have said in this, to move from the gross thickness of the reservoir to the pay thickness, and we will talk about this in the after a few coming slides, and how we identify the pay thickness. Selection of the cutoffs is also related to the process of moving from the gross to from the gross reservoir thickness to the pay thickness. The reservoir geometry, mainly if we want to know the reservoir geometry, it has to be done through multi-wells. It's a multi-well task. We cannot identify the reservoir geometry only through one well. So if we have multi-wells in the reservoir, by doing well log correlation, we can see the 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 geometries of this reservoir within the oil field. Now, a small introduction before going into details. We have talked about the oil field life cycle, and we said that it goes from exploration to appraisal, development and production, and moving from each step to another is requires specific type of information to be provided and be available to take us from one stage to another. And we will not go through that again. But the most important thing to highlight here is the concept of petroleum system. So we need to have both petroleum system element and process. So we need to have a mature source rock, and this oil field should have a migration path that connect both source rock to reservoir rock, and need to have suitable reservoir rock that contain both contain enough amount of both porosity and permeability, and we need to have a trap and impermeable seal, and this trap has to be sealed in order to keep those hydrocarbon from further migration. After the identification of structure, location is released for drilling. After the first well is drilled, so we are now in the process of collecting information in order to identify the worthiness of this well. Is it worth continuing, or we have to stop? So this information, even if the borehole is dry, for example, those information are still valuable. If we are unable to find hydrocarbon in that specific well, it doesn't mean that this information has to be thrown away or something. It can be helpful for in the future for any reasons. Till the time the well is being drilled, no one is sure that this well is containing hydrocarbon or not. So the only way to make sure that this borehole is containing hydrocarbon is after drilling. Now, what's logging and what do we measure? So, logging, we have give the description is electro logging or well logging, continuous recording of physical properties or parameters of the formation depth. And this definition is you don't have to memorize it. If you log in, if you take a look at the log sheet, you will directly identify that we are measuring physical properties in reference to the depth. And the primary objective of the well logging is to identification of the reservoir, estimation of hydrocarbon in place, and estimate of recoverable hydrocarbon. So we said that we can identify the reservoir thickness from the well logs, and if this reservoir are containing hydrocarbon, we can calculate or estimate the amount of hydrocarbon in place, and we can go further to even estimate how much of this hydrocarbon within the reservoir are recoverable, we can be produced. Because as we know, we cannot produce all the hydrocarbon within the reservoir. There is a limit, 40 to 50% it can be produced, and the rest is you need to do extra effort in order to take that out from the reservoir. Well log are results of several geophysical measurements recording the well. They consist of key information about formation drift. So we can identify productive zones of hydrocarbon, their physical properties, hydrocarbon like porosity, permeability, hydrocarbon and water saturation, and lithology. And we have seen how we can identify different lithologies in the wells by using the well log, the depth, thickness, formation, temperature, pressure of the reservoir, distinguish between oil, gas, and water zone in the reservoir, and measuring the hydrocarbon mobility. Now we have a different type of logging environment. It can be open hole logging, in which we don't have any casing in the borehole, and that is done in stable formation. If we have a very stable formation, which doesn't require any casing to support the wellbore. In addition to the fact that there are some logs that cannot be run in the cased hole, so we need to run those logs within the open hole in order to get proper information, because the tool has to be fixed against the borehole wall. We have the cased hole logging. In this case, casing is being installed and cemented in the borehole. This is the cement. The blue line is the casing, and then we can go and do our logging after the cementing. Perforation and production logging. So we have some type of logs that are done after the perforation, in which, for example, the cement pond log, in which we want to evaluate the cement job in integrity, if this cement is or the cement job is done well, and isolate unwanted interval, and whether the perforation is done correctly, and so on, before starting producing from this hydrocarbon, in order to avoid any problem or any accident in the future. We also talk about the type of casing. We have different type of casing that's being changed with different depths, and it's mainly done in the well planning. We plan for the first one is, for example, is the conductor. We have the surface casing, we have the intermediate casing, and we have the production casing. So this one is done in the surface in order to isolate loose surface sediment from being introduced into the borehole. Then we do cementing, then we put surface casing, and then we do another cementing, and then we cement the surface casing, then we put the intermediate casing, then we put a cementing for the cement for the intermediate casing in order to be fixed in its place. Then we put our drilling, our production casing, and then we cement this production casing in the last stage in order to prepare it for perforation and production. Now, what we can get from the logs. So this is the log. We have, as we said earlier, we have the different tracks. We have 4 tracks in triple combo. We have the first track, in which is we have SP, gamma ray, caliper, and the bit size. They are all in the first track. We have the depth track, which we have the depth values. We have the resistivity. It's mainly in the second track. It has a logarithmic scale, in which we have the deep resistivity, the shallow resistivity, and the medium resistivity. And then we have the porosity track, in which we have the neutron intensity and sonic. So based on those log, for example, gamma ray and SP, we can differentiate the sand zone from shale zone. And then from resistivity, we can differentiate the gas from oil and oil from water. So we have here the oil-water contact, we have the gas-oil contact, and using also the porosity log, we can identify the gas zones from oil zones, from water zones. So by combining the whole logs together and interpreting the whole logs together, we can get the entire information that we are that's needed for that specific reservoir. So we can have the depth, permeable formation, thickness of the reservoir, have the net sand and the base sand. We can get the subsurface pressure, fluid phases like oil, water, or gas. We can get the saturation, and we can calculate. There are many methods for calculating the water, the saturations. But as we said, the water saturation is the main important because it's essential for the calculation of hydrocarbon reserve. The movable hydrocarbon can be calculated from the saturation values, the depth of the formation, environmental of deposition. We have seen that how we can get it from the gamma ray response. The lithology is also from the SP and gamma ray. Temperature from the temperature log, the velocity and time. We can use the sonic log to generate an acoustic impedance, and from that we can get a synthetic seismogram, which is similar to seismic response, and that is very important in correlating the seismic to the borehole, because as we know, seismic is done in time, while the boreholes are in depth. So in order to fix them both, we need the synthetic seismogram and the correlation with other logs. So because the correlation is mainly done by the gamma ray log, one of the major logs for correlation. Now this is what I've described earlier, the moving from the gross reservoirs to the net bay. And as I said earlier, we are not interested in the entire borehole thickness. We only consider specific zones that are characterized by permeable and porous formation that can contain hydrocarbon. So we have this is the surface, this is the whole borehole section, and we have those shale intervals, and if we take a look at for example this log, we have those sand interval here, but those sand units are actually interrupted by some shale zones. So when we are talking about the gross thickness, in this part we are considering the whole sand thickness, whether it's containing shale or any other lithologies, but we are talking about the sand interval from its start to the end, regardless of the interrupting formation. This is the gross thickness or the gross reservoir. When we go to the net reservoir, which is the rock that can contain hydrocarbon, which has both porosity and permeability. So in this interval we are only talking about sand interval. So now we have moved from the gross to reservoir thickness to the net reservoir thickness. So in this part we are eliminating the impermeable interval. We are taking the shales out, and that gives us the net reservoir thickness. Now if we want to get to the net pay, we have to apply the cutoffs, and we have said that earlier, the cutoff value. And basically the cutoff values are the minimum accepted values for specific parameters. For example, we have porosity, shale volume, and we have water saturation. Those three parameters, they are very essential for identification of our zone of interest. So this zone, which is we are normally considered as a promising zone, it should have a specific limit of porosity and specific shale volume. Should not exceed that specific shale volume, because it will have negative effect in our porosity and permeability. And it also should have a specific limit of water saturation. It should not exceed that water saturation. So for example, if we have a reservoir, we will say if we have a net reservoir thickness, we will say, and we know that within this reservoir thickness, net reservoir thickness, there is variation in porosities and permeability. For example, the porosity in this section might not be the same as the porosity in this section. It will not be the same as the porosity in this section, because as we know, the environment is not fixed. It will not give you the same output. Even with the same input, the output might be variant. So as I was saying, we will have different porosity values in this section, from this section, from this section, from this section. We will also have different shale volume in this section, from this section, and then we will have different water saturation. The water saturation in this interval from here to here will be different from the water saturation in this interval from here to here. So we want, for example, only intervals that have porosity above, let's say 20%, above 20% porosity, and it has volume of shale less than, say, 30% volume of shale, and water saturation, let's say, below 25. Should have less than 25 water saturation. So in order to move from the net reservoir thickness to the net pay zone, we will only consider intervals here that have those three criteria. It should have porosity above than 20%, it should have volume of shale more than less than 30%, and it should have water saturation less than 25%. Only those intervals that have those criteria will be considered as a pay zone, which is a zone that contain hydrocarbon, and the hydrocarbon in this zone is producible. It can be taken out. If one of these criteria is not, so for example, if we came to this interval and we find that the porosity is 25, so it's acceptable because it's more than 20%. Our cutoff value is 20% porosity. So if it's more than it's 25, that means it's above 20%, and that's acceptable. We will evaluate the volume of shale. So if it has volume of shale, let's say for example 10, so it's less than 30%, and that's good. As we said, as the volume of shale decrease, that will make the reservoir more effective and more better. So if it has 10%, that make it a very good reservoir. But we came to the water saturation and we found that the water saturation is 40%, so it contains 40% water, and that will affect our hydrocarbon saturation, and that means that the hydrocarbon saturation is only 60%, and our cutoff value is 25, and it has 30%. So that means it's above our cutoff value, and that is not acceptable, so it will not taken as a net pay zone. So we will do the same evaluation for all interval in order to move from the net reservoir thickness to the net pay zones. Only the zones that have shale porosity and hydrocarbon saturation and water saturation specific values, and then in all the cases, as you said, we are moving from the very for example from 10 meter thickness to 5 meter in net reservoir thickness, and we can reach maybe 1 meter pay zone, and so on. I hope that make it clear, and if it's not, please let me know so I can go through it again, because it's very very important in reservoir in information evaluation. Now the evaluation step for any oil field or for any reservoir, there are several steps. So we have, before we do our formation evaluation, is actually one step in the entire evaluation step of the reservoir. So before we do our formation evaluation, we have to do a reservoir properties. So before we do our evaluation, because in information evaluation the main input is the logging tools, but in reservoir rock the main source of information is the rock, the core plugs. And those core plugs are taken in the exploration phase of the well. The first well that we drill, the wildcat, we do coring in different intervals, and those cores are taken to the lab and it will be analyzed for calculating porosity and permeability of the reservoir. Although it sometimes might be maybe more accurate than the logging tools, but there is some limitation. The first thing is that, as we said when we talked earlier about the core plugs, we don't take cores for the entire log. The cores are actually for the entire well. The cores are taken in different intervals. So we take it from one interval, we miss some part, and then we take it from another interval. So the data is not continuous, if you understand what I'm saying. We take it in some specific depths, then we might move maybe 5 to 10 meters and then take the other core plugs. So the data are limited in the amount because it's very expensive and so on. The second thing is it's not a real time. Those core plugs are taken by the logging tool, and then it will be packed, and then it will go to the lab, and then in the lab it will be analyzed, and this process might take very long time. It might take 1 month, it might take 2 months, it might take 3 months, and within this period of time the drilling operation will never stop. It will keep going. You cannot wait for the analysis of the core plugs to come in order to continue drilling, because we said that time is money in oil industry. You cannot leave the rig there waiting for 1 or 2 months, and you have to pay for it every day. So that's a lot of money. You will continue, and then whenever this data comes, you will correlate with whatever you have done or whatever you have get. So this is the first part of the evaluation steps, which is the reservoir rock properties. The second, after we done that, we go to the formation evaluation. So as we said, once we took our core plugs within drilling or after drilling, after we finish, we do our formation evaluation or logging. We install our logging tools, we take it down to the borehole, and then we start acquiring our data. In opposite to core plugs, logging data are unlimited, because we take the log readings for the entire section. It's continuous. We don't miss parts and do logging for some parts. It's done for most part of the borehole. The second thing, it's real time. As we are installing the tool in the borehole, we are getting our measurement. One drawback for formation evaluation is that it's a single well. Whatever we are getting, and I said that earlier, it's only related to the zone around the borehole. We cannot generalize whatever we are getting from this specific borehole to the entire oil field. So it's a single well measurement. After we done our formation evaluation for that well, we move to reservoir characterization. And in reservoir characterization, we rely on both logging tools and core data. But whatever we are getting from core plug in the previous stage and whatever we are getting from the logging tools, we use both of them in reservoir characterization. And the plus point or the advantage of reservoir characterization is that it's multi-well. We get those logs and core data from different wells in the oil field. We combine all of them together, and we use some field statistic to generate, for example, our 3D model. And in this 3D model, we can populate our porosity, permeability, rotability, cap pressure, saturation, relative permeability, and so on. So it will give us the bigger picture for our entire oil field. So this is in brief the main evaluation steps for any reservoir. Formation evaluation domains and services. We have, as I said previously, the integration. It's multidiscipline. We have petrophysical teams, we have geology team, we have geophysics team, we have reservoir team. Each team of these, or every domain or each discipline of these, have its own contribution in the entire formation evaluation process. The petrophysics used logs to give fluid saturation, porosity, permeability, and so on, and shaleness and lithology. The geologist gives the idea about the depths and facies distribution within the entire oil field or entire reservoir. Petrophysics, we can get the seismic, the structure within the reservoir or the oil field, and it's very essential in the building of the 3D model. Any 3D model start with geophysics. And reservoir formation testing and sampling. We can get physical samples from the reservoir. We analyze and study those physical samples, and we can also study the permeability of that specific reservoir. So the general goal of logs interpretation, we have lithology. As I said, there is specific logs that can give us an indicator about lithology and shale content, porosity, neutron density, and sonic, in addition to NMR, neutron magnetic resonance, composition, mineralogy, and so on. We have the saturation and fluids from electrical log, NMR, and permeability from acoustic logs. We said that triple combo is the main gamma ray, neutron density, and resistivity. If we find a log that contain those four logs, that's named triple combo, in which those logs are running together. The basic wireline log, this is a brief picture for the different type of logs and what we can get from each type of logs. Now we come to our phase 2. It's caliper. We have covered most of the logs before, so in this time we will only cover those new logs which has not been covered. For the caliper log, it's mainly used for identifying the borehole diameter and the variation in the borehole diameter with depth. So in a basic shape of the caliper log, it's that this is the tool and it has multi arms, and those arms are fixed to the borehole wall, and they are equipped with springs that is make it flexible and can be open and closed and moved freely with the variation in the borehole section and the changes in the borehole section. So there are many reasons that can cause the change in the borehole section. A washout, in which those intervals, for example, in shales, shales can be, or some other formation which are soluble in the drilling fluid. For example, they can do some create some caves in the borehole wall. This is why drilling, after drilling, after we finish drill, also there the drilling fluid can react with the formation, the rocks that compose the specific formation, and that can make it very loose, and it can cause some cavings or changes in the borehole section. Clay swelling. Clays are very well known with the fact that can swells and increase in volume after drilling, that can reduce the borehole section. So we have different type of caliber. We have 2 arm, we have 4 arm, we have 6 arm, and those arms are normally at 80 degrees to each other. So we have 1 arm here, 1 arm here, another arm here, another arm here. So this scenario is very rare to find, can only find in very hard or intact rocks. It can also be oval in shape. It can be circular, it can be oval, and but in most cases this is what actually we can see, the irregular cross section, and in this case we cannot evaluate the borehole environment or borehole cross section only using two arms. So we can go for 6 or 8 arms caliper log in order to give a clear idea about the cross section. And that is very important because when we are doing logging, we have to put the borehole condition in consideration, because it can affect the reading of some specific logs that are supposed to be fixed against the borehole, as we will see in the next coming slide. Some of the effects of the borehole condition in the log reading itself. So this is what we have been saying. We have single axis, we have 3 arms, we have dual axis, in which each 2 arms are at 180 degrees to each other, and we have 6 arms, which each 2 arms are at 180 to each other, but we have 3 sets of arms. Now, factor influencing caliper log. So we can, based on the caliper log, we can interpret the causes and the possibilities. So if it's in gauge or on gauge, that means there is no changes in the cross section or the diameter of the borehole. The cause, well consolidated formation, that's the formation is solid and intact and self-support, and non-permeable formation. So it's mean that it's a very hard rock that contain no permeability, and the possible lithologies for that is acid sandstone, calcareous shale, igneous rock, or metamorphic rock. If it's larger than the bed size, that means if we have a very high amount of cavings within the borehole section, that means the formation is soluble in the drilling mud. So the drill mud has the ability to solute the formation can be dissolved in the drill fluid, or the formation is weak and caving by itself. And this can happen in salt formation drilled with the fresh water. Fresh water can dissolve those salts and can create cavings, or either the unconsolidated sands or gravel or little shale that can collapse by itself in the borehole. If it's smaller than the bit size, if the borehole diameter is less than the bit size, so that means either the formation swells and flow into the borehole, that reduce the borehole diameter, or we have a development of mud cake, and that's happened in nearby the permeable formation. So if the formation swell, that we have swelling shale. If we have development of mud cake, mud filtrate, that means the formation is porous and permeable sandstone, because as we said, the invasion takes place only along the permeable and porous formation, which is sandstone. So the application of caliper log, we can identify the lithology, as we say in the previous slide. Based on the changes in the borehole cross section, we can get a clue about the different type of lithologies in borehole. A good indicator of permeability and porosity by the development of mud cake. As we see here in this interval, we have mud cake, and we can see here that the dashed line is the bit size. So there is a decrease in the caliper log, and that indicate a mud cake along a permeable sandstone. And the indication of hole quality or assessment of likely quality of other rock whose data quality is degraded by holes that are out of edge. And we will see an example for that in the coming slide. It's a collection of consolidated formation for wireline pressure testing, recovery of fluid sample, packer testing for well test purposes, and for determining casing setting depth. So it was a very important task or process that also can be rely on the caliper log and identifying of the lithologies along the borehole section. So we can calculate the mud cake thickness by the bed size minus caliper reading divided by 2. It can give us how much is the thickness of the mud cake within the borehole. This is the shale. This is the swelling, decreasing in the borehole diameter and increasing in the volume of shale that can cause this decrease. Brittle shale, or as we said, salts can dissolve or can collapse by itself into the borehole. The mud cake buildup and invasion process. The task of drilling fluid across the permeable formation is to prevent the invasion, the continuous invasion of drilling fluid along the permeable reservoir by building up of the mud cake or a filter cake along the borehole, and that will prevent those drill fluid from continuously going through the borehole, because I guess we talk about it in the first lecture. We said that after drilling complete, we do a well cleaning. We clean the well and those formation in order to prepare it for production. So with more invasion within the reservoir, that can block the pore spaces which in the permeable zones, and reduce both porosity and permeability, which is require more sophisticated cleaning technique in order to retrieve those porosity and permeability. Like in this case, as we see those oranges, the drilling fluid has been invaded, entirely invading the reservoir, and after it will keep precipitating in the pore spaces because the blockage of the hole, and as it's invaded, the formation is filtering the fluid from the solid particles. That's why it's called mud filtrate. So the formation will filter the fluids and block the solid particles, causing a very thick mud cake, and this mud cake can cause a very huge problems. It can stuck, the tool might stuck due to those very thick mud cakes, and that will cause an increase in the rig time, increase in the cost. So the accurate selection of the with the drilling fluid that can prevent the invasion is very essential in the drilling operation. Now this is an example of the effect of the caving in the log readings. So as we say here, this is the log. This is the logging tool. As we see, there is a very bad borehole environment here, very bad borehole condition. Those are very deep cavings. So those caving will be filled with shells from the drilling fluids, for example. So, for example, if we are running a density tool, a neutron tool, and as we know that density neutron tool is sensitive to hydrogen content, and those shells have very high hydrogen in them. So because it contains water, bond water. So when we come to the reading of porosity, we will find that there is a overestimation of porosity in specific interval. If we take a look at this zone, for example, there is the caving is almost, it has changed the diameter from this up to more than 16 inch, and if we check the porosity in this, it's more than 70% porosity, and this is mainly because the tool is reading the hydrogen amount in this zone. So the value of porosity in this log is not correct. It's due to the bad borehole environment in this section. So as we see here, most of the porosity values is actually more than 60 or 50% porosity, which doesn't make sense. And that's now those are two different interval to understand the effect of change in the clay content on the porosity. We can see here that this gamma ray value here is less than the gamma ray value in this one. And if we come to the Caliper Log and we see the amount of caving in this interval and the amount of caving in this interval, we can see that the caving in here is more, like the logs is reading even more than the 60 inch, while here it's around the 60 inch. So regardless the fact that the gamma ray reading here is low, so but because of the presence of shale here in the Caliper Log, that in this one the presence of shale in this interval cause a very high porosity value, which is not real at all. So the porosity value is not related to the gamma ray here, or not related to the lithologies in the gamma ray here, but it's related to the presence of shale in this interval. We have a high amount of shale here and that's caused the high reading of the porosity, and we have a high amount of shale here that cause the we have a less amount of shale here that reduce the amount of porosity in this interval. Now the Dipmeter log, it's more or less similar to the Caliper log. The difference in here that we can use this log to identify the dip of the formation. There are different type of Dipmeter. There is one which is it has the same principle of resistivity log. Give us it send current and receive it, electrical current, and then receive it in the receivers, and we have this log shape. So if we have the same response within the same interval, that's mean our formation is horizontal. So this formation is horizontal, this formation, and so on. But if we find any change in the depth of specific response, for example, if we have this response, for example, in this interval, so that means there are changing in the dip for that specific formation. This is an example for that. So we have pad 1, 2, 3, and 4, and this is pad 1, 2, and 3, and 4. So this is, if we imagine that it's a cylinder and then we cut it and open up the cylinder, so we have this formation here with this horizon in this place. In pad 1 we see that the response of the pad is in this specific depth, which is here. Okay, and we come to pad 2 and we see that the response of the same formation is giving upwards, as we see here. So this is the pad 1, which is related to this one, and we have pad 2, it's a little bit higher, and pad 3, it's more higher. This is pad 2, this is pad 3, it's more higher than pad 2. And we have pad 4, which is in equal depth to pad 2. So we have pad 2 and pad 4, which are at 80 degrees to each other, 180 degrees. This one, 2 and 4, they are at the same depth, 2 and 4. And we have pad 1 and pad 3. This is pad 3 at very higher or very lower depth than this one, which is at higher depth than. So that indicates that our formation is dipping, and in order to calculate the depth, the dip angle, we take the diameter of the borehole, and we have the distance from the lowest part of the formation intersection to the higher intersection of the formation with the pad, which is 6 inch divided by 2, through the tan of the value is 27. So the dipping angle for this horizon or the formation is 27 degrees, and we know that each pad is actually pointed to specific direction, so we can also get the strike and dip direction. If we know the strike of the formation, we can directly get the dip direction, which is always perpendicular to the strike. So this is in brief how we can get the dip for any form of formation or horizon based on the Dipmeter. Another type of, or another version of caliper Log is the formation micro imager, and this tool is very good tool because it can give us a core like image for the borehole. As we see here, we can visualize an entire core the borehole without doing a coring job. So we can evaluate the depth if the horizon is vertical, if it's horizontal, or it's dipping, and we can also analyze any variation in the composition within the borehole. This is a clear image. This is the true outcrop, and this is the FMI. This is done for research 15 meters behind the outcrop. So we have this outcrop. They did the FMI image 15 meters behind the outcrop, and we can see clearly how similar they are. Succession of the formations in the image can be easily correlated with the true formation image, and can easily be interpreted, and we can see the horizons very clearly. Now we come to the gamma ray. We have already talked about the gamma ray and principle and its application before, but we want to highlight the volume of shale calculation, or the clay volume calculation, to be more accurate, because it will be used for the reserve estimation, in the equation of the reserve estimation. So if we have this as a gamma ray log, we have the minimum gamma ray and we have the maximum gamma ray, which is called, this is the sand baseline and this is the shale baseline, which is connected the highest values of gamma rays, which is called the shale baseline, and the line that connects the minimum gamma ray value, which is called the sand baseline. So this is one represent the maximum gamma ray, and this one represent the minimum gamma ray in the equation. And we have the gamma ray log is the gamma ray reading in a specific interval that we need to find out the clay volume. So if we need to calculate the clay volume in this interval, for example, we will read the value of gamma ray, which is 90. We will put it in this place. We have gamma ray minimum, which is 35. We have gamma ray maximum, which is 135, minus gamma ray minimum, which is 35. So that makes the gamma ray index equal to 90 minus 35 divided by 135 minus 35, and that gives us a specific value for gamma ray index. In most cases, most petrophysicists assume that the gamma ray index is equal to volume of shale or volume of clay. But to be more precise and more accurate, we have to change this gamma ray index into clay volume, and that can be done by this graph here. We have volume of shale in the clay volume in the y-axis, and we have gamma ray index in the x-axis, and by finding the intersection of that specific gamma ray index with one of the lines here, and we can get the volume of shale. So there are different equations. Those lines are actually, in reality, they are empirical equations. They have been tested and by testing the correlation between the gamma ray index and clay volume in different values, and they came up with those line. So each line have its own specific condition. So for example, if we are dealing with older rocks, we will go for Larinov. So for example, if we have a value of gamma ray index of 0.6, so the equal volume of shale is around 0.48 or 0.49. So, and if we have tertiary rock, for example, so we will take a straight line, and then the intersection with this line, Larinov, tertiary rock, you'll find that the amount of volume of shale is around 2.5, or clay volume is around 2.5. So we have to know which type of formation or which type of lithology we are dealing with, and which type of condition we are dealing with in order to pick the accurate equation. Otherwise, assuming that gamma ray index is equal to clay volume is not correct. It's not wrong, but to be more precise, and if you have more information about the lithology, you can go for any of those equations. So that's, by that we reach our the end of this lecture. The next lecture we start with porosity and whatever we have more to cover in this lecture. I hope it was clear for all of you, and I'm very welcoming any queries or questions regarding this, regarding whatever we have covered in this lecture. So whatever is not clear, we can go through it again. Thank you for listening, and have a nice day.